thermal current and electric current. This is the second lecture of your thermal conduction. In the first lecture, we have seen how to write the equation of the thermal current, and before watching this lecture, I expect that you must have gone through lecture 1 of thermal conduction. Now we are starting with the comparison of thermal current and electric current. See, in electricity, we see that if there is a conductor of length L, okay, and say the area of cross section A, and there is a potential difference across the two ends, say delta V is the potential difference. So because of the potential difference, electric current will flow. Say I is the electric current and I is the rate of flow of electric charge, dq by dt. The unit is coulomb per second, which is given the name ampere, okay. So if you compare the thermal flow with the electric charge flow, so let us see the first thing. In the electric charge flow, what is the parameter which decides the direction of current? So that is the potential difference, correct? Positive charge spontaneously flows from high potential to low potential. Positive charge spontaneously flows from high potential to low potential. So potential difference is the parameter in electricity which determines the direction of flow of current. We have seen in thermal flow, what is the deciding factor which will make predictable what will be the direction of flow of heat? That is the temperature difference. Heat spontaneously flows from the region of high temperature to the region of low temperature. So whatever the role is being played by the potential difference delta V in electricity is the similar role played by the temperature difference delta T in thermal flow. Now what is the quantity that is flowing in electric current? That is the electric charge denoted by Q. And what is the quantity that is flowing in thermal current? That is the heat energy, again denoted by Q. It has a unit of joule, it has a unit of coulomb, okay. How we define the electric current? I dq by dt, rate of flow of the electric charge, correct? How we define the thermal current? H dq by dt, the rate of flow of thermal energy. SI unit will be joule per second, that we have seen watt. We write the electric current as what? Potential difference divided by the resistance. This we have been studying right from the lower classes. The electric current is what? The potential difference by resistance. Now just think how you write the thermal current, H. So instead of potential difference, what will be appearing in the thermal current? It will be the temperature difference, correct? And R will also be R. Here it is the electrical resistance, here it is the thermal resistance. That is the difference in the name. Both are resistance. It is offering the obstruction in the flow of electricity, it is offering the obstruction in the flow of heat energy. It is also called the R value. Here the unit will be ohm, we all know. R will be volt per ampere, which is given the name ohm. And here if you see what will be the unit of R, so if you make R as the subject, so R will come to be temperature by thermal current, that is Kelvin per watt, okay. So this is the comparison chart of what? The thermal current and the electric current. Now let's see what is the thermal resistance. You know, resistance is the property of the object and resistivity is the property of the material. So what it means, if you have different pieces of copper, say a rod of copper, a block of copper, a container of copper, so you can see the material is same, isn't it? All have the same material. So when all have the same material, your resistivity will be same, because resistivity is the property of the material. And we will see conductivity is 1 by resistivity. So if resistivity is the property of the material, conductivity will also be the property of the material. Resistivity is usually denoted by rho. But resistance is not the property of the material. Resistance is the property of the object. So they may have different resistances, whether it is thermal resistance, whether it is electrical resistance. Got it? So whenever you talk about resistance, we talk it for a particular material like this piece of copper, this rod of copper. But when we talk about resistivity or conductivity, we talk for the material like the resistivity of copper, the resistivity of aluminium. Got it? So I guess this is clear that resistance is the property of the object and resistivity or conductivity is the property of the material. Now write in electricity, we write rho as the resistivity and R as the resistance and sigma as conductivity. Okay? In thermodynamics or thermal flow, rho is again your resistivity, but conductivity is denoted by small k. Okay, and you know, resistivity is 1 by conductivity. Here you can write resistivity is 1 by k. And in thermal flow, most of the formulae will be more appearing in terms of the conductivity. So this is the quantity which will be appearing in most of the formulae. So if somewhere resistivity is coming, what you can write? 1 by conductivity. Okay? So in thermal flow, conductivity is denoted by the symbol small k, that is the property of the material, and resistivity will be denoted by rho, and of course your rho will be 1 by k. Got it? Now let's see, suppose we have a uniform slab. Suppose we have a uniform slab, or you can say slab of uniform area. Got it? As we have seen in lecture 1, when the current flows, the penetrating area may be uniform or non-uniform. That I told you how to analyze, and that is very critical step. So suppose we have a slab like this, okay, and at this point, right now I'm talking about electric current. Okay, right now let's see, we are talking about electric current. This is the area, and here the potential is V1, and this surface, the potential is V2. So current will flow between the surfaces where there is a potential difference. Current flows between the surfaces where there is a potential difference. So here you can see there is a potential difference between the right and the left surfaces. So current will flow like this. So if I talk about what will be the area that is being crossed by the current, if this area is A, so can I say every time the current is moving, it is crossing slices of area A. So your area is uniform, okay, and say the length is L. So the length traveled by the current between the two surfaces of potential difference, the length traveled by the current between the two surfaces of potential difference is L. So we have seen in electricity the resistance of this object is rho L divided by A. This is the formula for the resistance, electrical resistance of this object. And this formula has one limitation. This is applicable when your area is uniform. Got it? This is very important limitation of this formula. Like in this case, you can see the area is uniform. So in the same way, now we can define thermal resistance, or you can say the R value. Okay, now we can define a thermal resistance, or you can say the R value. Got it? So suppose we have a slab of uniform area. Again, I'm repeating. The limitation is area is uniform. We will see shortly if the area is non-uniform. We will apply calculus. Right now, this surface has a temperature T1. Got it? And this surface has a temperature T2. And this length is L. And this area is A. Okay? So, as we discussed in lecture 1, step 1 is analyze what will be the direction of thermal current. So while analyzing the direction of the thermal current, we have to see what are the two surfaces which are maintaining the temperature difference. So in this figure, clearly you can see the two surfaces are the right and the left surfaces. So current will flow between the right and left surfaces. So your current will be flowing, either you can label left to right or right to left, as we have seen in lecture 1. When you will apply the equation of the current with algebraic sign, it will also give you the direction. So this will be the direction of thermal current. Now step 2 is you have to analyze whether the current is penetrating the areas which are uniform throughout or variable in nature. So if you cut out the slices, you will see each area is rectangular and is constant. Say this area is A. So when the current is flowing, each slice will have the area A. So your area is uniform, correct? How much? A. So this is a uniform area propagation of current. So here you can define the thermal resistance as the resistivity, same as the electrical resistance, L divided by A. Now as I told you right now, in thermal flow, what is the parameter of more discussion, more common use is conductivity, K. And K is 1 by rho. So if you want to write this formula in terms of K, your resistance will come to be L by K into A, isn't it? So this will be the formula for the thermal resistance in terms of K. And there is one limitation of this formula. What this limitation is, the formula is applicable for uniform area. Got it? So whenever we have some uniform area conduction, you can apply this formula. What is L? Here L denotes the length over which the current is flowing. L denotes the length over which the current is flowing. What is A? A is the area of the cross section through which current is penetrating. Now I will give you some of the illustrations which will make it more clear how to apply this formula, correct? And K is the conductivity, which is of course the property of the material. Remember one point, the same object may have different resistances between different surfaces. Very important point. The same object may have different resistances between different pair of surfaces. So while finding the resistance in any object, you have also be clear ki across which pair you are finding the resistance. See the illustration. Suppose we have a block, okay, and this length is A, this length is B, and this length is C. Now if I say find the resistance of this block, if I say find the resistance of this block, that will be meaningless statement, because you will say you will put the query across which surfaces. So see, for the same object, see part A, or I am writing 1 just to avoid double use of small a. Between left and right surfaces, okay, between left and right surfaces. What it means between left and right surfaces, that if the temperature difference is maintained between left and right surfaces, then what is the thermal resistance it will offer to the flow of thermal current. So when you are going to find the thermal resistance between left and right surfaces, it means when the temperature difference will be maintained, it will be maintained across left and right surfaces. Though it will not be given as T1, T2. You will just be told to find the resistance between left and right surfaces. So you can imagine, in that case, the current would be flowing between left and right surfaces, something like this. So in this case, what will be L? What is the length that is traveled by current? That is A. What is the area? So if you visualize, just cut the slice through which the current is going. So your slice would be something like this, with a length of how much? C, and the breadth is B. So area will be B into C. Is the area uniform? If you cut any slice, will it seem like this? Yes. So area is uniform. So you can apply that formula of resistance. That is L. What is L? A, conductivity K into area BC. This will be the answer for this part. This will be the answer for this part when you are finding the resistance between the left and right surfaces. Now see the second part. If in the same object we are being told find the resistance between top and bottom surfaces, okay? Now what is the meaning of top and bottom? Now the temperature difference has to be maintained between top and bottom. So in this case, what do you think? Where the heat will flow? The heat will flow across the surfaces having the temperature difference. So heat will flow like this, isn't it? So in this case, what do you think? What is the length covered by the heat? That is B, this much length. What is the area? Now if you see the area which is penetrated by heat has a length A, breadth C, so area will come to be AC. Is the area uniform? Yes. So since area is uniform, you can apply resistance as length divided by conductivity into area. So this is the formula. Now can you see the very same object? There is no change in the object. The very same object is giving you different resistances between different pairs. The object is same, the same block. When you are finding the resistance between the right and left surfaces, the resistance is coming to be A by KBC. When you are finding the resistance between the top and bottom, the resistance is coming to be B by KC. So the resistance is not only the property of the object, it is also the property of the pair of surfaces through which the heat current is flowing. Are you getting the point? It is also the property of the pair of surfaces through which the thermal current or heat is flowing. So whenever you are finding the resistance, be clear about the two surfaces across which the heat will flow. That the length between the two surfaces will give you the value of L, and the slice area, cross-sectional area, will give you the value of A. Got it? Now suppose we have a cylinder, hollow cylinder, okay? Something like this. And this is of some material, and say this is the axis, and this is the inner radius A, and this is the outer radius B. Now if I say simply find the resistance of this hollow cylinder, it makes no sense, isn't it? You have to define the surfaces. So suppose if I'm saying find the resistance, see, if I'm saying between inner and outer surfaces. What it means? It means that the inner surface of cylinder is at some particular temperature. Are you getting the point? This whole inner surface says at a temperature T1, and this whole outer surface is at a temperature T2. In lecture 1 I told you how the heat will flow. Now the heat will flow radially, isn't it? Let us choose the color orange. So heat will flow like this. We are making a 2D figure. but actually the heat flow will be radial in 3 dimensions between the inner and outer surface. Okay, so heat will be flowing like this. If you see the cross-sectional view, so something like this will be visualized, and heat will be flowing between the inner and outer surface like this. So what will be the area that is penetrated by the heat? It will be the cylindrical envelope, isn't it? In this case, it will be cylindrical envelope, say of radius r, and so the cylinder has a length L. So area penetrated by current will be 2 pi RL, that is cylindrical envelope. Now can you see the area is variable, isn't it? Your area is variable because as the heat is moving from your inner surface to outer surface, every cylindrical envelope is changing in the radius. So here we have variable area. So this formula of thermal resistance has no applicability. We cannot apply this formula. Okay, we will have to apply calculus. We will see right now shortly how we will apply. But before that, let me find the resistance between the two end surfaces, or you can say left and right surfaces. This is, see, again the object is same, but the pair of surfaces are different. So here you will say, okay, it means now the temperature difference will be maintained across the left and right surfaces. This is different from this situation. In this case, heat will be flowing like this, traveling how much length? L. Now here you will say, let's analyze the area which is penetrated by heat. So we'll see an annulus. If you make the cross-sectional area, so it will come to be of inner radius A, outer radius B. So area will be pi B square minus A square. And wherever you cut the slice, here, since the heat is flowing like this, it will remain uniform. So in this case, you can apply the resistance formula. Length by conductivity into area. Here you can apply when you are finding the resistance of the cylinder between the end surfaces. When you are finding the resistance of the cylinder between the end surfaces, and the very same concept, the very same calculation, the very same formula will be applicable in electricity. Only the name is changed. This is the thermal resistance, that will be the electrical resistance. So here you will say the resistance is, what is the length? L, K, and what is area? Pi B square minus A square. This will be your answer. So this is very straightforward problem, correct? Very, one step problem. When you are finding the resistance of the cylinder, uniform cylinder, between the end surfaces. Where? Between the end surfaces. Got it? Okay. Now, let's see how we can solve this problem. Now, since in this problem, when you are finding, be careful about this thing, because as I told you, not only it will be useful here, but the same approach, same formula will also be useful in your class 12 syllabus, electricity. If you are finding the resistance of the cylinder between the inner and outer surface, we cannot apply this formula because the area is changing. So what we'll do, we will take a cylindrical shell of radius r, okay? So suppose we have this cylinder, and this is radius A, and this is radius B, okay? And this is some material of conductivity K. Take a cylindrical envelope or cylindrical shell like this. Let me take a little bit thickness like this. Okay, say cylindrical shell of radius r and thickness dr. Now the thickness is very small. Through this cylindrical envelope or cylindrical shell, the area will be what? So you can write the current is crossing a length, how much? dr. So the length traveled is dr, isn't it? Because the current is going like this between the inner and the outer surface. So T1, T2. And what is the area cross? 2 pi RL. So suppose the resistance of this cylindrical shell or segment is dr. So dr will come to be length traveled dr, d small r, divided by conductivity into area. Okay, so this will be the resistance of this cylindrical segment, yellow one. So we have applied the calculus. Now, of course, between the inner and outer wall, there will be a number of such cylindrical envelopes or cylindrical segments or cylindrical shells in continuous manner. And all the resistances will be in series. So for total resistance, you will integrate R beginning with the limit of A and R ending at the limit of B. So it will come to be dr divided by K 2 pi RL from A to B. Okay. So R will come to be K, conductivity is constant, 2 pi is constant, L is constant. What is left is 1 by R dr from A to B. So I'll get 1 by 2 pi KL ln R within the limit A to B. So we'll get 1 by 2 pi KL ln B minus ln A. Apply the property of log. So we'll get 1 by 2 pi KL ln B by A. So this is the answer. This is the resistance of the cylinder between the inner and outer surfaces. Got it? Now this you can also remember, as I told you, this is not only used in thermal flow but also in electricity. If there is a cylinder, we can also remember as FTP. Okay. And it is also possible that, to make problem more application oriented, K may also be variable. Here see, K comes out of the integral. If the examiner want to check more of your conceptual clarity, K may also be given as a function of R. So in that case, K won't come out of the integral and this FTP will not be applicable. So here if K is constant for the material, it is not changing with R. So between inner and outer surfaces, your resistance is 1 by 2 pi KL ln B divided by A. Got it? This is the FTP for the resistance of a cylinder between the inner and outer surfaces. Between the two surfaces, end surfaces, there is no need of calculus, we have seen. We can directly apply this formula. This one. That's a one-line problem. Got it? Okay, now see the next application. In the same way, suppose we have a sphere, hollow sphere. And the inner radius is A, outer radius is B. And say it is filled with or made up of a material of conductivity K. And we have to find the resistance between inner and outer surface. Okay, we have to find the resistance between inner and outer surfaces. So it means there will be some particular temperature of, say, inner surface and some temperature of, say, here, outer surface. So the temperature difference is between the inner and outer surfaces. So heat will be flowing between inner and outer surface. Again, the direction will be radial, isn't it? It will be 3D. I'm making a 2D cross section. So can you visualize what will be the area shape of the surface through which heat will cross? So it will be a spherical surface. Like in the previous problem, it was a cylindrical surface. In this case, it will be a spherical surface of area how much? 4 pi r square. So as the heat is going from inner surface to outer surface, what do you think? Is the heat passing through area of uniform cross section or non-uniform? So of course, if r is changing, a will be changing. So here again we have non-uniform area. So this formula, length by Ka, has no applicability because this is limited formula for uniform area. So again we will apply calculus. So what we will do here, we will take, like in the previous problem we have taken a cylindrical shell, here you will take a spherical shell or a spherical envelope of radius r and thickness dr, and this has a resistance dr. So dr will be what, as we have seen in the previous problem, the length. The length is dr, the thickness which is being passed by current. Dr is the thickness, can you convince, which will be passed by current and passing through this orange spherical envelope. Conductivity into area. So it will be dr by conductivity into 4 pi r square, correct? So this is your dr. And infinitesimal resistance of this spherical envelope. So what will be r? You have to integrate. So you'll get dr divided by k 4 pi r square. Now 1 by 4 pi k will come outside being the constant. What is left is 1 by r square dr. So it will be 1 by 4 pi k r minus 2. So it will be minus 1 by r, isn't it? Within the limit a to b. So your r will come to be, I can take minus outside, 1 by b minus 1 by a. So I'll get minus 1 by 4 pi k a minus b by ab, and if you remove the minus outside, reverse the order, so 1 by 4 pi k b minus a by ab. This is the answer. So this is the resistance of a hollow sphere between inner and outer surfaces. Got it? This you can also remember as FTP. If there is a hollow sphere with inner surface A and outer surface B, so this is the resistance between inner and outer surface. The same formula will be applicable in electricity, the electrical resistance of a hollow sphere. There we usually write, K is 1 by rho. So in electricity we write the formula rho by 4 pi B minus A by AB. Okay. In thermal flow, we usually prefer the parameter conductivity. In electricity, we usually prefer the parameter resistivity. Okay. So this is how we find the resistance when the area through which current is flowing is changing throughout continuously. Then we can't apply that formula. R is equal to L by Ka. Okay, now let's see when the resistors are in series. So the same concept is applied in electricity, the same concept is applied in your this thing. Say this is R1, this is R2, this is area may be same or area may be variable, that doesn't matter. For the generalized case, I'm making the variable area, and this is temperature T1 and this is a temperature T2 and this is R3. So of course the heat will flow across the regions of different temperatures. So heat will flow like this, correct? So you can see the resistances are in series. So whenever the resistances are in series, number one, they have the same current, same thermal current, number one property, always remember. Of course, the temperature will change continuously. Say this temperature is T dash, this temperature is T double dash, okay? But each cross section will have same thermal current. So your net resistance will be, like we do in current, it will be the sum of the individual resistances. So in series, in sigma notation, you can write sigma Ri, I begins with 1, runs till N. The same concept of your electricity, okay? Whenever the resistances, the slabs are connected like this, forming the series formation, so every cross section will have the same thermal current, and the net resistance will be the sum of the individual resistances. Got it? Now see, finding the temperature of the interface. This is also very common problem and application. You can mark it important. Suppose we have two slabs, okay, like this. In this case, they have same area. Let the area be okay, A1 and A2, and we will take the special case of same area. That will be better. So there are two slabs with area A1, A2. Got it? Here the length is L1, here the length is L2, here the conductivity is K1, here the conductivity is K2, and we have to find, this is the junction, common boundary, interface, common interface. So we have to find this temperature. So say I'm making a generalized figure. So this temperature is T1, this is your T2, okay? And of course heat will flow like this. You can make either from T1 to T2 or T2 to T1. This area is say A1 and this area is say A2. And this is what? This is the common interface or junction. And say here the common interface is a temperature theta, which we have to find. Here the conductivity is K1, here the conductivity is K2, this length is L1, this length is L2, okay? So see, can you say this is the series combination of two slabs? Number one, can we say, you can write the heading, okay? The heading is that the goal is finding the temperature of interface, or common boundary or common junction. So key point one is, can we say both the slabs are forming series combination? Yes. So if they are forming the series combination, the current, thermal current will be same. So if here the thermal current is H1 and in this slab the thermal current is H2, so surely you can say H1 is equal to H2. Why? Series combination, correct? Now what will be H1? So I'm applying that thermal current equation, Fourier law with algebraic sign. So if I'm applying the thermal current equation with algebraic sign, so I'll put a negative sign, the conductivity, that is K1. Temperature difference will take how much? First write the area A1, final temperature, that is theta minus T1 divided by L1. And what will be H2, conductivity K2, area A2, final temperature T2 minus theta divided by L2. Okay, so let this be equation 1, 2, 3. Now what we have to do? Now rest is mathematics. Put equation 2 and 3 in equation number 1. So what we'll get? H1 is equal to H2. So minus K1A theta minus T1 by L1 is minus K2A2, this is A1, T2 minus theta by L2. Now this will get cancelled away, cross multiply. So I will get K1A1 L2 theta minus T1 is K2A2 L1 T2 minus theta. So I'll get K1A1 L2 theta minus K1A1 L2 T1 is K2 L2 L1 T2 minus K2 A2 L1 theta. Now what is the goal? You have to find theta. So make theta as your subject. So I'm bringing this theta term on LHS. So I'll get theta multiplied by K1 A1 L2 plus K2 A2 L1 is equal to K2 A2 L1 T2 minus will be plus K1 A1 L2 T1. So theta will come to be K2 A2 T2 L1 plus K1 A1 T1 L2 divided by K1 A1 L2 plus K2 L2 L1. This is your answer. Got it? This is your answer. This is the expression for the temperature of the common boundary. Now if you take a special case, if area is same, okay, suppose we have two slabs, this has a conductivity K1, length L1, this end has a temperature T1, this end has a temperature theta, and this is your T2, and area is same, say A, this length is L2, conductivity K2. So your calculation, your expression will get more simplified. Now A1 is equal to A2. How much? A. So this equation will become, I guess all A will get cancelled away, K2 T2 L1 plus K1 T1 L2 divided by K1 L2 plus K2 L1. So in many of the MCQs, you will find that both the slabs have the same area. So that will be more easily calculated. Either you can take that case as a special case of this thing, or you can derive it from beginning here only, and your area will get cancelled away in this equation only. That's your choice, okay? If you remember this FTP, then you will take it as a special case of this FTP, making the area same. Or suppose if you don't remember the FTP and the area is same, so you can derive it from the very basic step, okay, taking the same area, so area will get cancelled in this very equation, okay? So this is the skill how we find the temperature of the interface of two slabs connected in series. Got it? Now see, like in this figure, you are given, there are two slabs, okay? I'm giving you this as a homework. This slab has a conductivity 3K, and say this slab has a conductivity K, and this area is not given, we will assume it's same by the figure, and this length is say L, and this is 2L, okay? And here we have a temperature 20 degrees Celsius, and here we have a temperature 120 degrees Celsius, and this is the interface. So you have to find part A, the thermal resistance of each slab. Let the area be A, because when you will be finding the thermal resistance, area must be given in the problem, okay? So let the area given be A. So can you find the thermal resistance of each slab? The equivalent resistance, so when you will get R1 and R2, now since there is a temperature difference between the right and the left surfaces, so resistances are connected in series, so the equivalent resistance will be the sum of R1 and R2. The rate of flow of heat, thermal current through any slab. Now you have to find, because why any slab? Because the thermal current or rate of flow will be same in both the slabs, isn't it? So that's why it is being told through any slab. Or even if it is not given through any slab, simply the demand is find the rate of flow of heat or thermal current, so you can find through any slab. So after finding part A and B, you have to find the thermal current, which will be flowing like this. And of course your answer, main valve K, main valve L, main valve A, right? We don't know the temperature of the interface. So this problem, illustration 3.1, I am giving you as a homework. You will do and submit in the written notes, okay? Make sure to submit Complete it and submit in the notes at this place. Now let's see the meaning of equivalent thermal conductivity. See, what is the meaning of equivalent thermal conductivity? Suppose we have three resistors R1, R2, R3 within the temperature difference T1 and T2, and the current flowing is H, and it has a thermal conductivity K1, it has a thermal conductivity K2, it has a thermal conductivity K3, correct? Now just remodel the situation as we find the equivalent resistance. Remodel the situation. If you are making a single slab across which that same temperature difference is maintained as across the combination, as across the combination, and the total length would be this, and say area is A. So if the same heat is flowing through this slab, if the same heat is flowing through this slab, say H, and it is a conductivity K, so this K is called the equivalent conductivity of these three slabs. Got it? This K is called the equivalent conductivity of these three slabs. So this is the meaning of equivalent thermal conductivity. Got it? Now let's see how we apply it in the problem. Suppose we have two slabs. One of length L1, one of length L2. It has a conductivity K1, it has a conductivity K2, and the area is A, and we have to find the equivalent thermal conductivity. Got it? We have to find what? Equivalent thermal conductivity. So write their resistances. What will be R1? So R1 will be L1 K1A, and what is R2? We will say L2 K2A, correct? And this is the total length. And say we need not to write the temperature difference, but if you want just for the imagination, you can think the heat is flowing like this, then only they will be connected in series. Now I have to find equivalent conductivity. So forget that there are two slabs. Make a single slab occupying the complete length. Make a single slab occupying the complete length. So this length would be L, isn't it? And same heat must flow through it. And say this imaginary slab has a conductivity K and area will be same A. So here the resistance will come to be what? Here resistance will be L by Ka. Okay. Now this equivalent resistance is the equivalent of these two resistances, isn't it? This single slab is playing the role of equivalent conductor having same resistance as effectively offered by the combination of these two. So this is a series combination. So we can say R is equal to what? R1 plus R2. So I'll get Ka is L1 by K1A plus L2 by K2A. Now A will get cancelled away. Now what will be L? So L is the total length. So in place of L you can write L1 plus L2. So therefore L1 plus L2 by K is what? L1 by K1 plus L2 by K2, correct? So you will get L1 plus L2 by K is coming to be L1 K2 plus L2 K1 divided by K1 K2. Now make K as the subject. So your equivalent conductivity will come to be what? K1 K2 divided by L1 K2 plus L2 K1, and you will get this thing multiplied by here L1 plus L2. So this will be your answer. This will be your equivalent conductivity. Got it? K will be K1 K2 L1 plus L2 divided by L1 K2 plus L2 K1. So this is how you find the equivalent conductivity when two slabs are connected in series. Already I have told you if areas are different, then also if this is R1, this is R2, the current will be same. So if here the current is H1, here the current is H2, H1 will be equal to H2. Now R1 will be equal to what? L1 by K1 A1, and R2 will be equal to what? L2 by K2 L2, and they are connected in series, so it will be R1 plus R2. So see a problem from JEE Main 22. Here you are given, there is a steel, here we have a furnace at 450 degrees Celsius. There is a steel rod, and then we have copper, and there is ice box at 0 degrees Celsius. And of course this is given some insulating material, so there is no leakage of heat. Even if insulator is not given, we will assume in ideal case there is no loss of heat to the surrounding. K1 and K2 are the thermal conductivity. So they have their thermal conductivity K1 and K2. A1 and A2 are the area. Okay. And you are given K2 by K1 is 9. A1 by A2 is 2. L1 by L2 is 2. That means conductivities, areas and lengths are related. They have a certain ratio. And you have to find the temperature of the junction. What will be the temperature of this junction? This is the problem. Say theta. This will be what? Okay, now tell me, can you work it yourself? Right now we have seen this kind of problem, isn't it? I guess right now we've seen this here. It's similar problem like this, isn't it? This one. We have two slabs with different areas, different conductivities. So we got this as the temperature of the junction. Finally, we derived this formula. Correct? And in this JEE problem, A1, A2 are related, L1, L2 are related, K1, K2 are related. So of course, your common parameter will get cancelled away and you will get the answer. So I guess you will be able to work out this problem, work out with working and submit in the notes. Okay? JEE 22. Now say the temperature of the junction. In many of the problem, suppose we are given, this is again no new concept, simply conservation of energy. Suppose we have three rods like this. This has a temperature T1, this has a temperature T2, this has a temperature T3. This length is L1, this length is L2, this length is L3, this area is A1, this area is A2, this area is A3. And this is the junction or node. This is called a junction or node. And you have to find the temperature of the junction. Okay? So say if you apply the conservation of energy, energy can neither be created nor be destroyed. And thermal current is what? Thermal current is simply the flow of thermal energy. So the net thermal current coming to a junction will be equal to the net thermal current going out of the junction. So you can write net H incoming equal to net H outgoing. And same thing will be, applicable in electricity. Here you are writing thermal current, there you will write electric current. That is will be called Kirchhoff's law. I don't know where the current will flow. You can assume any model. Okay? So I'm assuming here the current is going like this. You can say, okay, sir, what if I label outward? You can label. Accordingly, your algebraic sign equation will take care of. Here the current is H2 and here the current is H3. So this is H1, H2, H3, correct? Now you can write what? Total current in is equal to total current out. So I'll get H1 plus H2 is what? H3. Now what will be H1? So H1 will be what? Minus K1, say it has a conductivity K1, it has a conductivity K2, it has a conductivity K3. Into area A1 temperature difference, final theta minus T1 divided by length L1 plus minus K2 A2 theta minus T2 divided by L2 is equal to minus K3 A3. Now the final temperature is T3 minus theta divided by L3, and you will get the unknown quantity, correct? You will get the unknown quantity. Okay, in most of the problems, the calculation will be even easier for you. In most of the problem, we have something like this. They are of same material. So K is same. Same area. So area is also same. Now if this is T1, this is T2, and this is T3, this is theta. And so this length is L1, this is L2, and this is L3. And this temperature is theta. So now you know, in your equation, you will get something more convenience. So this is H1, this is H2, and this is H. So again the same equation will hold. Incoming current is equal to outgoing current. So H1 plus H2 will be equal to H. So we'll get minus K, A is same, theta minus T1 by L1 plus minus K, A, theta minus T2 by L2 is equal to minus K, A, T3 minus theta divided by L3. Now see, this will get cancelled away and we'll get the theta. Sometimes you know even L are related. Suppose this is L, this is L, this is 2L. So also you will get more easier calculation. So this is the fundamental while finding the temperature of the junction, okay. Now see this problem, IIT Advanced 2001. 3 rods of same material having the same cross section have been joined. Each rod is of same length. So many things are made convenience for you. They have same length, correct? This is 0 degree, this is 90, this is 90, length is same, area is same, material is same, so conductivity will be same. And you have to find the temperature of the junction, say theta. Okay, so can you work out this problem? You can assume here the current is coming, here the current is coming, here the current is leaving. So this is H1, this is H2, this is H3. So your equation will be H1 plus H2 will be equal to H3. Work out and submit in the notes. Very easy problem, that is from IIT 2001. You know, in this case, IIT has given you the data. So many things will get cancelled on both LHS and RHS. K will get cancelled, A will get cancelled, L will get cancelled. Your calculation will become quite easy. So this was the lecture of thermal conduction, slot 2 or second lecture of thermal conduction. In the third lecture, we'll be doing more problems with the thermal resistances, and now we will see the parallel combination and doing some more problems of the PYQs of JEE Main and Advanced, okay.